need this. Okay, so again, guys, these are the 5 or the 4 that you are doing. You know me well enough, and you probably picked up on this from what I said. Guys, these 4 were picked very strategically. Because guess how I'm going to teach you ions? Guess how I'm going to teach you noble gas abbreviations? Guess how I'm going to teach you Lewis dot structures? By using these as a foundation for our conversation. So not only is this a great opportunity for you to fine-tune your understandings, it's also going to be the rock upon which we're going to build everything you're learning today. So I'll give you another minute to get these done. If you have questions, we'll talk about them. I'll show you the answers. And then, guys, we're just going to pick these 3 things off one at a time. You're going to learn about ions. You're going to learn about noble gas abbreviations. You're going to learn about Lewis dot structures. Now, guys, here's the neat thing, is after today, no more drawing arrows. Yay! That was my official no more drawing arrows dance, and most of you missed it. And I'm not doing again. I'm like Beetlejuice. I won't do 2 shows a day. Tell me that any of you caught that reference. Beetlejuice, I won't do 2 shows a day. I won't do it. One of the finest movies ever made. You guys all seen Beetlejuice? 3 Amigos? Can I confess to you publicly that when I saw 3 Amigos in the theater, you know the opening segment of 3 Amigos where they're riding on their horses and they're singing the 3 Amigos song and they hold that note for like forever? I got up and walked out of the theater. I'm like, I cannot sit through this. And I got up and left, and then I rented it, and now it's my favorite movie in the whole wide world. It's the only movie, I must have been in a bad mood, but I got up and left, and I know. I walked out on Chevy Chase in one of his finest moments. I know. Now he's stuck doing Community, which is not that funny anymore. Not anymore. Oh, he's not there anymore, is he? Okay, sorry guys, I'm being wildly distracting and this is being recorded. I should shut up. Do these. Good heavens. Worse than you guys. Morgan, are you feeling like you're understanding that idea of separating the arrows? Good. You guys all, you need another second? Alec, is your head about to explode? Okay, did you watch the screencast? Okay, you may pick up on a little bit of this as we go through this today because some of this will be looking backwards. But you're going to want to get on top of that screencast and probably come in and ask questions tomorrow. Yeah, you missed a ton of stuff. You guys all caught up? You okay? Do you know how to do these?
Yeah. I started drawing, so that's why.
You can have mine. So guys, let me give you sodium just to make sure we're on the same path. Sodium would look like this. One in the you got the 1s, then the 2s, and the 2p. Those are all full. Then you've got 1 electron in the 3s for a total of 11. And many of you, I think, picked up on this idea that the way to error check these is look at the 3s, and sodium is the first box in the 3s, which means it'll have 1 arrow in the 3s. Yeah? Yeah. All right. May I give you chlorine, or is that too fast? Here's chlorine. Chlorine has 17 electrons. Notice, guys, that similarly, chlorine has 1 empty box, and it is 1 square, if you will, short of the end of that 3p. So we would expect it to have that 1 empty electron spot in the 3p. You guys okay on chlorine? Can I give you copper? Or too fast on copper? 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 Here's copper. Good on copper? Good? Again, guys, similarly, copper is one box away from the end of the 3D, and we have one empty spot in the 3D. Can I give you, here's arsenic, there's all of them. So guys, I'm going to give you about literally another minute, which feels like an eternity when you time it, but we'll go for another minute. And then the assumption is that if you're not asking questions, you guys are all here with me, and we will move forward into the 3 things you've got to learn to do today. Yeah. That was both ignorant and rude. Yeah. But here's the thing. Sorry.
It wasn't meant to be.
No, and understand it was neither of those things to me. But what you have to understand is that all of and a lot of this stuff drives me nutty, but our brains are all wired differently. I mean, there are things that you can do that I could never get close to. You have a group of skills and abilities and talents that are unique to you that make these easy for you.
I guess just the way you introduced it made it sound like this was going to be like hard.
No, but here's the thing that you don't understand. There are people in this room right now that have no clue what they're doing. And several of those people came and got help from me this morning, but I sat down with several people at 7:15 this morning that were so completely lost. And they had been through the same day, they're not in this class, they had been through the same day that you did on Tuesday, not a clue. So, yeah. Eric owes you an apple fritter. Okay? So, if he offended you, me too. Go ahead, sorry. Hey guys, actually, in all seriousness, let's wrap this up so we can move forward. Go ahead.
So, if it's really like the last category that really matters.
Right. Yes. Good for you. And so let's use what you just said as our segue. So guys, now we are, in all seriousness, going to move forward. And here's the deal. Sawyer is exactly right. And that is one of the 2 things I would suggest to you that makes these tedious. Not only are you drawing a lot of arrows, which in and of itself stinks, but nothing changes until you get to the end. It's a horrible waste of time. So why do I ask you to do it? Because it reinforces the concept. If I hadn't done that, Morgan wouldn't have asked, why is it that these go unpaired until that one, where did it go? Oh, it was in the homework, until that one actually has to pair up. She, you, all of us need to know that. So you've got to draw the orbital filling diagram so that you understand what's going on behind the scenes. But now that we are all there as a group, we're not going to do this anymore, and we are going to get rid of the stuff that is technically a waste of time now that you know what's going on. That's what we're going to do next. You guys ready to go? Okay. So guys, this is hurdle number 1. The first thing that we need to do is we need to go back a month, remind ourselves what are ions, and then apply those concepts to what we now know. So let's reach backwards, bring that knowledge forward, and then apply it in this new situation. So guys, what is an ion? Take notes as you need. What is an ion?
It's a charged atom.
Good. It's an atom with a charge. Now, guys, you may remember that when we have atoms that have a charge, we have an imbalance of protons and electrons. Remember we did the chart, the protons, neutrons, electrons? We have an imbalance of protons and electrons, but we don't form them by changing the number of protons because that changes the identity of the element. So how do we do it? Well, guys, remember there's 2 types. You guys all remember that a cation has which charge? Positive or negative? Positive, because the T looks like a plus sign. You all remember that cations are positive, and in order to form a positive ion, do we add or remove electrons? Remove, and then conversely, we have these negative ions, which we call anions, and these are negatively charged, and we form those through the addition of electrons. Is it all coming back to you? Okay, now, to help you really firm up your memory, please don't write this down. You may remember something like this. This is the way you were originally introduced to this concept. We said chlorine atom, and we came over here and we found out that chlorine is element number 17, and we found out that its mass is 35, and from that we were able to figure out 17 protons, 18 neutrons. Then we said, how many electrons? Well, it's the same as protons, and that's 17. And then, guys, we started to play these games. And we said, what if we want chlorine with a -1 charge? What do? We not take away, we add an electron, and then it's 18. And then we said, what if we want to make this chlorine with a +1 charge? And what do? We take one away. But guys, again, check this out. If we want to go chlorine +1, this would now be 16 electrons, so we take one away, right? Y'all with me? Because here's the question. Which one? Which one do we take away? Because it used to just, and I ask it rhetorically because the answer is not obvious. Guys, we can't just anyway take away electrons. Because now we know more about electrons. We know they're not in a circle. That's the Bohr model. We know there are 17 of them, but they're organized like this. So which ones do we add and which ones do we remove? And Jared, this gets to your question a moment ago about reactivity. And guys, the answer is this. When we add or remove electrons to form ions, the ones that we add or remove come from the highest S and or P sublevel. And these have a name. They are what are called the valence electrons. And valence means on the outside. So again, guys, the idea is this. Because we now understand that these electrons are not lumped together in a pile, we still need to be able to talk about adding and removing electrons, but we've got to talk about which ones. And the answer to which ones is or are the highest S and or P electrons, and those are what are called the valence electrons, which simply means they're on the outside. Y'all caught up with me? Okay, now guys, take those ideas and play along with me here. You ready? This is sodium, yes? Look at sodium. And guys, do this in pencil. You're going to be doing a lot of erasing. What if we want to go sodium -1? What do? Be careful here, guys. What do we do sodium -1? Do we add or remove an electron? We add it and we put it right there. So that would be sodium -1. Now, what if we want to go sodium -2? How many electrons do we need to add? 2. So one goes there. Where does the other electron go? There's nowhere for it to go, which means that sodium cannot go -2. There is a limit to the charges that these atoms can take on, and on the test on Monday, you are going to be asked to identify what those limits are. So, can sodium go -1? Can it go -2? No, there's nowhere for it to go. Now, guys, let's go the other direction. Whoopsies. I don't know what happened there. Guys, let's go the other direction. Let me see if I can write. Hold on a second. I'm going to ignore you for a minute, Kyle. Now, guys, let's do this. Let's go sodium +1. In order to do +1, what do? Take away that electron, and that would be sodium +1. Now, guys, what about sodium +2? Which 2 do we take away? This one And which other one? None. Guys, go back and look at your notes. Which are the valence electrons? The highest S or P. And once we have identified energy level 3 as highest, energy level 2 is no longer the highest. So can sodium go +2? It cannot. Now let's do questions. Kyle, go ahead.
So would adding it making you go +2, would that be just a totally different element?
It's not a different element because remember the identity of the element is based solely upon the protons in the nucleus. So for example, try this. Guys, we're doing electrons. And guys, check out Kyle's question because this is huge in the next chapter. Kyle said this: if we go sodium +1, we take away this electron, right? So what's left? A full 2p, which would be the electron structure of neon. So if we go sodium +1, does it turn into neon? No, but it has the electron structure of neon. It does not behave, well, it sort of behaves like neon. But guys, what you're going to find out is this, and this is right at your question, Jared. Whenever an atom bonds, what it's trying to do is gain or lose electrons so that it can take on the electron structure of one of these. Because guys, what's magic about these? They're all full up, and we call them the noble gases. So sodium will try to lose this electron and take on the structure of neon. We'll talk more about that in the next unit. You guys okay? So look down here at chlorine. Chlorine -1. Let's keep going for a second. Chlorine -1. We add an electron right there. And by the way, guys, when chlorine -1 does that, what does it then take on the electron structure of? Argon, right. Now, guys, what about this? Chlorine -2. Can't do it. There's nowhere to put the second electron. Can't do it. Now, guys, what about this? What about chlorine +1? Which one do we take off? Not that one. Guys, they come out opposite the order they went in. So they went in 1, 2, 3, 4, 5. So which one do we take out? That one. So Sawyer, here again is a reason why we need to do the orbital filling diagrams, because if we didn't, we wouldn't know which one to pull. Okay. Now guys, what about this? Chlorine +5. Can we do it? Yeah, take all of these away. What about chlorine +6? Can we do it? Yeah. Highest S or P, y'all. It's not just the P, it's also the S. So we can take all of these and that. What about chlorine +7? Can we do it? Second. Yeah. We've got all of these, 5, 6, 7. We can take them all. What about chlorine +8? That we can't do because we've only got 7 electrons in the highest S or P. Now let's do questions. Go ahead. Exactly. And so what's happening is this. When you peel this one so what you said is correct. Now let me explain why. When you peel this one electron off the S, what you're doing is you're exposing nothing but full orbitals. And those full orbitals are so stable that you can't pull electrons out of them. And they're full, so you can't put electrons in them, so they're done. Yeah. Go ahead, Pickle.
So it has to be like 3p and 3s for you to like.
Correct. Yep. Exactly. But remember, if you've got a P, you've got to have an S. But if you've got an S, you won't have a higher P because the P always comes after the S. Did that make sense?
So it's only like
Exactly. That's right. Talmadge, go ahead. Let's do that in just a second because I picked these on purpose, didn't I? Yeah. Go ahead.
So if you were to take off 7
Yes.
electrons,
Uh-huh.
have the electron structure of the
Exactly. Yes. Yep. Exactly right. Go ahead, Michael.
So I've noticed that the
Sorry. Oh, you know what? Hold on. I've actually got to quit this. It's being really weird. Go ahead and keep talking and I'll...
where you took out for the chlorine, when you took out 7, they were all from the same energy level.
Yes.
So when you're going
And not just, yes, they have to be the same and the highest. And so the thing is if you've got if the S is the highest, you won't have a P. If you've got a highest P, you've got to have an S as well, because the P's fill after the S's.
Once you take all of those out from one energy level,
Yeah, then you're done. You can't go deeper. And that's what we were talking about with Stirling, that once you pull those outer ones off, everything underneath is so stable they can't move. Yep, go ahead. It does. So let's call them orbitals, those clouds. The clouds cease to exist. Well, good question. So how do we represent that? What we'll do is, say for example we were doing sodium plus 1. Let me just rewrite this. What we would do is we would go 3s in an empty box. We would show it as being empty, meaning it would have been there, now it's gone. You okay? Okay, so now let's go. Who was saying what about the deeper ones? Talmadge, right? Let's go deeper. So guys, take a look at copper, okay? Copper minus 1. What do? Where do we put the electron? There's space there. Can we do that? No, it is not the highest S or P. Copper cannot go minus anything. It doesn't have space in a highest S or P. So what about copper plus 1? Can we do it?
Yeah.
That electron right there, because the highest is the 4s. Can copper go plus 2?
Yes.
Take them both. Can copper go plus 3? No. Go ahead, Jared. Did we get it? You guys okay? All right. So what about this? Guys, this is what this question might look like on the test. What are the range of charges that arsenic can take on? Oh boy. So guys, let's try it. Can arsenic go minus 1? Hold on, follow along. Can arsenic go minus 1? Yeah, we can put one there. Can it go minus 2? Yes. Can it go minus 3? Can it go minus 4? No. So arsenic can go down to minus 3. Now what can it go up to? Can it go plus 1? Take that away. Can it go plus 2? Yeah. Can it go plus 3? Yeah. Can it go plus 4? Yes. There. Highest S and P. So it can go plus 4. Can it go plus 5? Can it go plus 6? No. So the range of charges for arsenic are from minus 3 to plus 5. Go ahead, Lou.
So the most you can take out or add is
Yes. Theoretically, yes. But understand that actually never happens, because when they have 8, they are so stable that they neither gain nor lose. They could, they just don't because of their stabilities. But correct. But what you're saying, but in practice, actually they range from plus 7 to minus 7 because they never gain or lose 8 electrons. But what you're saying in theory is correct. Yeah, go ahead.
So if you take out all of the, you take out 5 electrons, then
And that's what I was talking with Eric about. What we would do, how would we represent arsenic plus 5? We would draw the 4s orbital empty and these orbitals empty. Yeah. You okay? Okay. So guys, now you ready to get rid of arrows? Here we go. We are now moving forward. The next thing in your notes you want to write down is NGA. Oh, it came back to you. Look at that. Okay, so guys, we are going to have an open, honest conversation about why we get really sick about drawing orbital filling diagrams. Sawyer and I have already kind of had this conversation, but let's have it again. What is painful about orbital filling diagrams? The arrows, and they're crazy, stupid, redundant, right? 1s with 2, 2s with 2, 3s with 8. It's the same stupid thing all the time, and they never change until the end. Well, guys, we are now going to get rid of both of those problems. But don't write this down. In doing so, we've got to be careful that we don't get rid of useful information. So, guys, let me tell you now. we are going to find a way to communicate all the same information, but in a way that is not a wild waste of time. But again, as Sawyer and I were saying, guys, understand that it's only a waste of time if you understand the orbital filling diagrams, because you can conceptualize what's really going on. With that said, here's how they're different. When you draw noble gas abbreviations, oh, thank goodness, no more arrows. You are now done, except for the test on Monday, you are now done drawing arrows. So what are we going to do instead of arrows? We are going to count up the electrons, and we are going to make them a superscript in the structure that we're going to draw. So the number of electrons will become a superscript. So that's one problem out of the way. But guys, the other problem, the other thing that we hate about orbital filling diagrams is we've always got to start back here in the 1s. What a pain in the tail. So guys, let's give ourselves a little more freedom. Instead of starting at hydrogen every time, we are now going to start at the nearest preceding noble gas. And we sort of talked about this already. These are the noble gases, the ones on the very far right. Guys, what's special about the noble gases? They're all full up. So they provide a bedrock upon which we can build these structures because they're all full up. Good? Okay. So guys, with that done, let's go back here, and now we are going to turn these into noble gas abbreviations. You ready? Do this with me. Sodium, and you guys can write this out here. Guys, sodium is right here. Do this with me. Here's sodium. Guys, which noble gas does sodium come after first? Neon. And guys, watch. Where's neon? End of what? 2p. So here's what we're saying. All of this is neon. So what we're going to do is we're simply going to write neon, and then in addition to that, we've got the 3s sublevel. Now guys, how many electrons are in that 3s? 1, superscript, done. That's nice. Yeah? So let's do that same thing to chlorine. Guys, when we do chlorine, and again, notice I picked these really carefully. When we do chlorine, can we go to argon? It's got to be the preceding noble gas, which again takes us to neon. Oh boy. And by the way, guys, these have got to be brackets. They cannot be parentheses. So neon, and then in addition to that, we've got the 3s with how many? 2. And the 3p with 1, 2, 3, 4, 5. That would be chlorine. Good? Okay. So now, guys, let's do copper. Here's something a little different. Here's copper. Which noble gas do we go back to? Argon. So, guys, argon takes us through here. So we've got argon. Again, that goes in brackets. And in addition to that, we've got the 4s with 2 and the 3d with 10, and that would be argon.
Why are they called noble gases?
Because they're standoffish. They don't interact. You guys okay? Hold on. Guys, the D can hold 10. Right? Please don't make this mistake on the test. Promise? Because guys, this is wrong. You're going to start writing these down quickly and blindly, and you're just going to go, oh, the D holds 10. Yeah, the D can hold 10, but here it's only got 9. So this would not be 3D10. This would be 3D9. Go ahead. Yeah, good question. Let's do the last one, and then let's talk about this. So guys, let's do arsenic. Arsenic goes back to argon, so that gets us through here. And guys, forgive me, I'll write it up here. So then what we've got is argon, and then in addition to that, we've got the 4s with 2, the 3d with 10, and the 4p with 1, 2, 3. Ah, did it work? Cool. You guys all okay? Okay, go ahead. Yeah. Those are called orbital filling diagrams. Yeah. Okay, so guys, did you catch what Jared said? I sold these noble gas abbreviations to you as something simpler. But I would propose to you that right now what we've actually done is we've only created more work for ourselves. Because all that we've done up until now is drawn the noble gas abbreviation based upon the orbital filling diagram. That's not less work, it's more. So what we've got to be able to do is we've got to be able to draw the noble gas abbreviations without the orbital filling diagrams. So let's learn to do these without doing the orbital filling diagrams first. So here we go. Find magnesium on your periodic table. It's number 12. Now guys, watch. Here's how you do them. Magnesium is here. Which noble gas do we go back to? Neon. So we're going to go neon, and then check this out. Which sublevel are we in? The 3s, and it has 1, 2 electrons, so it's 3s2, and we're done. Nice, huh? Okay, guys, let me just tell you right now, I am going to ignore your questions until I'm done with these total of 4 examples. Don't talk. So here we go. Gallium is right here, right? Which noble gas do we go back to? Argon. Then, in addition to argon, we are going to go these 2 electrons, which are where? 4s. So that would be 4s2. Then we've got these 10 in the 3d. And then we've got the 4p for 1, like so. Now guys, let's do some ions. So we are looking at iodine. For iodine, we go back to krypton. Again, make sure it's in brackets. And then in addition to krypton, what have we got here? 5s. 2. Be careful, guys. That 2 has got to be a subscript, or I'm sorry, a superscript. Then we've got 4d with 10. And then we've got the 4p with 1, 2, 3, 4, 5. Oh, sorry, 5p, my bad. Then we've got the 5p with 5. Now, guys, this is iodine without a charge. But we want to make this iodine -1, so what do? Add an electron, and this then becomes a 6. You okay? Now, guys, let's do this. Strontium with a +2 charge. Strontium is right here. So we go back to krypton. And then in addition to that, guys, we've got the 5s with 2 electrons. But now we want to give this a +2 charge. We take away 2. Now, guys, here are your options. This is fine. You can put 5s0 or 5s nothing. This is fine. You can put 5s0. This is not okay. You don't get rid of the 5s altogether. So 5s nothing works. 5s0 works. Just don't erase the 5s. Okay, hold on. So guys, I want to do this carefully. I want to answer questions. So if you have a question, let's answer it. If you have an observation or an aha moment, save it for a second. So let's do questions. Go ahead. No, I won't. Not anymore. Frankly, if you went back and looked at the homework where I taught you ions in that table, most of them were not possible. But you didn't know any better, so I got away with it. But now you know better, so no, I won't give you any that are impossible. Any other questions? Yeah.
Give us like the noble gases.
No, so maybe, but here's the deal. When you do the noble gas abbreviation for a noble gas, you have to go back to the previous noble gas. So for example, the noble gas abbreviation for argon would be neon 3s2 3p6. Y'all good? All right. Now does anybody want to share the aha moment? Really? All right. Then I'll get to do it. Grab your periodic tables. Guys, you see magnesium, neon 3s2. Grab your periodic tables, look at magnesium, squint really small and look below the big Mg. These are all on the periodic table. Oh. Number 12. Someone help Jared. Oh, they're all on there. Now, guys, allow me to warn you about something. Use this as a help, but not a crutch. Because, guys, the order that the periodic table authors put these in is different, and in this class, wrong. Let me explain to you what I'm saying. Guys, for example, if you look at gallium, up here, the first 2 electrons go in the 4s, then 10 electrons go in the d, then 1 goes in the 4p. That's the order that they fill. Now look on your periodic table, and for gallium, it says argon 3d10, 4s2, 4p1. They are out of order, and if you write that down on the test, I will mark it wrong. So now let's talk about why do the authors of this periodic table do it that way? What does it do the way that they're doing it?
Screws everything up.
Makes it so the valence electrons are together. They put the valence electrons at the end so they're easier to identify. They put the 4s and the 4p together at the end. We are not going to do that. We are going to put them in the order that they fill. So if you blindly copy these off the periodic table, you will get many of them wrong because the authors of our periodic table use conventions that are not the same as ours. Groovy? You're going to do these. Yep. All right, guys, one more to learn and then we're done. LDS, which has a whole nother meaning here where we live. These are what are called, guys, Lewis dot structures. Heaven forbid you would ever become a chemist, but if you do, there's this guy in the world of chemistry named Lewis who was an electron obsessive freak. He loved electrons. Everything that you will learn about electrons through your first 3 years of chemistry in college will all map themselves back to this dude, Lewis. So guys, Lewis came up with another way to draw atoms. And here's what he did. He focused on the valence electrons. Now guys, which electrons are the valence electrons? The highest S and P. And why are they important to us? They're important because they're the ones that are on the outside and they're the ones that do the reacting. So when Lewis came up with this idea of Lewis dot structures, he was only looking at the valence electrons because those are the ones that get involved in bonding, which is what we're doing in the next unit. So how do these work? Well, he allowed dots to represent the valence electrons, and then he put those dots around the abbreviation of the element. So guys, don't write this down, but follow along. Literally, don't write this down. You can't keep up and you're going to miss it. So here's the idea. Guys, which electrons are the valence electrons? Highest, S, and P. So here we go. What's that one right there? That's the S. This is the P's. Now guys, this is review. How do we place these electrons? Well, electron 1 goes there. Where does electron 2 go? paired up. Now where does electron 3 go? Here. Now what about electron 4? And that's what we were talking about earlier. Electron 4 goes here, 5 goes there, then 6, 7, and 8. You good? Okay. Well, guys, now we're going to take this same progression, and instead of drawing arrows, we are going to draw dots. And instead of drawing them all in a horizontal row, we are going to take these 4 boxes and surround the abbreviation of the atom. So, fictitious element XX. Here's what we're going to do. We are going to take the box for the s orbital, and we are going to imagine as if it's there. And then we are going to take the 3 boxes for the p orbitals, and we are going to imagine as if they are there. But we're never going to draw the boxes. You have the mental picture of where they are, but we are never going to draw them. So they're gone. But in your brain, they're still there. So guys, what's up here? The S, and the first electron, just like this, goes there. Where does the second one go? With it. Just like the second arrow goes with it. Now, guys, we've got our 3 boxes, and we could put electron 1 there. Does electron 2 go there? No, it's really electron 4. No, it goes unpaired. And then 5 goes there. And now what about 6, 7, and 8? They pair up just like these. Good? Let's do that with this. Here we go. So guys, let's do sodium. So sodium goes like this. Write the abbreviation of the element. Now, how many valence electrons does sodium have? 1. All done. That's the Lewis dot structure for sodium. You're done. But now, guys, let me show you this. The s orbital does not have to be on top. You can put it anywhere you want. So this would also be a valid Lewis dot structure for sodium. The only way that you can screw this up is to put the Lewis dot on the corner. Top, bottom, left, right. Did you notice I did that right for you? Left, right. It's funny I do that. Guys, doesn't matter. You just can't put them on the corners. So now let's do chlorine. Chlorine is Cl. How many valence electrons does it have? 7. So here we go. 1. Where does 2 go? Paired up. Then we go 3, 4, 5 unpaired. And then 6 and 7 pair up. And that would be the Lewis dot structure for chlorine. You ready for the aha moment? Check this out. Look, sodium has 1 dot. Look, chlorine's got 1 hole. Look, sodium sticks its electron in there, and what do we get? Table salt. That's what we're doing next unit. Now, guys, copper. Be careful here. How many valence electrons does copper have? Just the 2 in the s. So is this okay? Yeah, it doesn't matter where they are. It just has to be a pair. Then, guys, finally, and I'll do it up higher, arsenic. Arsenic has got how many valence electrons? 2 and 3 for 5. So we can go 1. Where does electron 2 go? Paired up. Then 3. Where does 4 go? Unpaired. Where does 5 go? Unpaired. That is 1. You just have to have 1 pair and 5 unpaired, 3 unpaired electrons. Now, guys, the Jared question. How on earth do we do these without the orbital filling diagrams first? Well, guys, see if you can figure this out. You see sodium? How many dots does sodium have? 1. Look at where it is on the periodic table. Now, see chlorine? How many dots does it have before we move this one in? 7. See where it is on the periodic table? You see arsenic, we're going to skip copper. See arsenic? How many dots does it have? 5. See where it is on the periodic table? Do you get it? Arsenic is 1, 2, 3, 4, 5 boxes into the P. Chlorine is 1, 2, 3, 4, 5, 6, 7 boxes into the P. Sodium is 1 box into the S. So guys, their position on the periodic table gives you the number of dots. All of these have 1. And by the way, guys, guess what that means? They all react the same. All of these have 2. All of these have 3, 4, 5, including arsenic, 6, 7, including chlorine, and 8. So now, guys, what about the D's and the F's? Well, are the D or F electrons valence? No. But in order to get to the D and the F, we've got to fill the S first. So just like with copper, copper's over here, but the only valence electrons it has is from the previous S. So how many dots will all these have? And that's it. You get the idea? Ah. Yeah, but these are still 2 as well. Those are all 2. Yes, because to get there, you've got to go through the S first. So guys, let me offer to you a suggestion on this homework. Uh-oh. Good heavens. Can't even count to 4. Okay. Guys, this is my suggestion to you on the homework. Well, read the directions. It says, write the noble gas and then the Lewis dot structures. Here's the hazard. If you do that the whole way through the assignment, you're going to get to the point where you can't draw the Lewis dot structures without the noble gas abbreviations. So here's what I would suggest. On the front, do the noble gas, then the Lewis dot. On the back, do the Lewis dot, then the noble gas, so that you learn to draw the Lewis dot structures without the noble gas abbreviations first. We will grade these on Monday. We will turn in the extra credit on Monday, if you choose to do it, and then we'll take the test on Monday. Yeah?
So with neon,
Yep,
when you want to do the noble gas structure, do you use neon?
you do.